Hello students, this is your chemistry teacher. Today we are going to discuss the following topics of group 16 elements, oxides and their classifications, preparation and properties of ozone, allotropic forms of sulfur and their properties, preparation and properties of sulfur dioxide, oxides of sulfur and their structures, and sulfuric acid and its preparation. So let's get started. The first of all the oxides are classified into four categories: acidic oxide, basic oxide, neutral oxide, and amphoteric oxide. In case of acidic oxides are those oxides which combine with water to give acid. As for example, sulfur dioxide is an acidic oxide that combines with water to give sulfurous acid H2SO3. So sulfur dioxide is an acidic oxide. Moreover, oxides which give bases after combining with water are called basic oxide. Like calcium oxide is a basic oxide that combines with water to give calcium hydroxide, that itself is a base, right? Moreover, there are some oxides which have dual behavior. They behave as acid, at the same time they behave as base, and moreover they react with both acids and bases to give their corresponding product, such as aluminum oxide. Al2O3 is an amphoteric oxide. Here aluminum oxide can react with HCl acid to give this species aluminum H2 whole 6 3 plus, that is acidic in nature. And at the same time aluminum oxide Al2O3 reacts with NaOH base to give this species Na plus AlOH whole 6 3 minus, that is basic in nature. There are some oxides which are neither acidic nor basic. They are called neutral oxides. Like nitric oxide is a neutral oxide, carbon monoxide, nitrous oxide, N2O, these are all neutral oxides. Now let's come to the preparation and properties of ozone. So first of all, what is ozone? Ozone is the allotropic forms of oxygen that is quite reactive. Moreover, ozone forms a protective layer in the atmosphere. As we all know, it forms a protective layer, so that to prohibit the entry of UV radiation to the earth, right? How is it prepared? It is prepared by passing ozone is prepared by passing silent electrical discharge through a stream of oxygen. As you can see over here in the reaction, when we pass silent electrical discharge or electric current, you can say in simple words, through a stream of oxygen, then we can get ozone, O3 molecule. Okay. uh, what are the properties of ozone? Properties of ozone. In the properties of ozone, the most important property is the ozone is the one of the strongest oxidizing agent. Why is it called strongest oxidizing agent? Because ozone on decomposition gives a nascent oxygen, where this oxygen atom or this oxygen is very much reactive, and this oxygen is available for other compounds to oxidize them. As for example, if I oxidize lead sulfide with ozone, then the nascent oxygen of ozone will oxidize the lead sulfide and it will form lead sulfate with the liberation of O2. Now this is the structure of ozone, where we can see there are two resonance structures in which ozone can exist. Here central oxygen atom is connected with two oxygen atom by double bond and single bond respectively. Here also the same kind of situation in structure occurs, but these two structures are interconvertible by resonance, and this is the actual structure of ozone. That is called the resonance hybrid of ozone molecule, and these two structures are the two resonance structures of ozone. So ozone has bent structure, as you can see over here. Ozone has a bent structure, and these two are resonance structures of ozone. Now let's come to the different allotropic forms of sulfur and their properties. Sulfur mainly exists in two allotropic forms. First of all, one is rhombic sulfur or alpha sulfur, and secondly monoclinic sulfur or beta sulfur. What are the properties of rhombic sulfur or alpha sulfur? Rhombic sulfur is yellow in color. Secondly, it is soluble in carbon disulfide solvent but insoluble in water. Whereas in case of monoclinic sulfur or beta sulfur, this monoclinic sulfur or beta sulfur are the high melting allotropes of sulfur, and it is soluble in carbon disulfide. Now, what is going to happen in both alpha sulfur and beta sulfur? Sulfur atoms exist as S6 form and S8 form. In the S6 form, the B structure is the S6 form, where 6 sulfur atoms are combined to form a molecule, and this molecule has chair like structure. Okay, so this is one form of S6 molecule, and this molecule, sorry, this molecule is the S8 molecule, where 8 sulfur atoms are uh, combining together to form a crown shaped structure. This is a crown shaped structure, and this is a chair like structure. In both alpha sulfur and beta sulfur, this S6 form and S8 form of sulfur are present. Now let's come to the preparation and properties of sulfur dioxide. What is the laboratory preparation of sulfur dioxide? Sulfur dioxide is mainly prepared by treating a sulfite solution, SO32 minus, a sulfite solution with acid, or you can say by acidifying the sulfite solution we can get easily the sulfur dioxide gas with the liberation of water. What are the properties of sulfur dioxide? Mainly sulfur dioxide, as we have already discussed, that sulfur dioxide is an acidic oxide, and so it will combine with water to give acid like sulfurous acid H2SO3. Moreover, sulfur dioxide react with sodium hydroxide or sodium hydroxide to give sodium sulfide or sodium bisulfide. Sulfur dioxide mainly reacts with water or base to give sodium sulfide or sodium bisulfide. Here you can see that sodium hydroxide react with sulfur dioxide to give sodium sulfide Na2SO3, and at the same time Na2SO3 reacts with water and sulfur dioxide to give sodium bisulfide. Okay, now what is the main property of sulfur dioxide? Main property of sulfur dioxide is reducing property. It can reduce various species like iron 3 plus, 2 iron 2 plus, or it can reduce potassium permanganate solution to colorless manganese 2 plus. If I take iron 3 plus solution, if I take a solution which contains iron 3 plus ion, and then if we pass the sulfur dioxide gas, then iron 3 plus will be reduced to iron 2 plus and sulfur dioxide will be oxidized to sulfate ion. Okay, at the same time, if we add sulfur dioxide or if we pass sulfur dioxide in a violet color solution of potassium permanganate or in a violet color solution of MnO4 minus, okay, then what is going to happen? Then the color violet color of permanganate will be fade up, or violet color will be vanished, and the solution will turn into a colorless solution of manganese 2 plus. So this is one kind of observation of sulfur dioxide. If sulfur dioxide is present in a medium, then what we can do, sulfur dioxide in that sulfur dioxide medium, if we add a manganate ion or permanganate solution, violet color permanganate solution, and if the color of the solution is changed to colorless manganese 2 plus solution, then you can see yes, in the solution probably sulfur dioxide is present. Now the most important part of this topic is the structure of sulfur dioxide. The structure of sulfur dioxide exists as two resonance structures, as you can see over here, where sulfur is the central atom, and sulfur is connected with two oxygen atom by double bond and a single bond. Both these two bonds are are involved in resonance, as you can see over here, that these two structures are interconvertible structures, they are resonance structures, and due to this resonance the sulfur oxygen bond length is neither a single bond length or nor a double bond length. The sulfur oxygen bond length, it has been observed that sulfur oxygen bond length is in between single bond length and double bond length. Why is it happening? It is happening because of resonance, because sulfur and oxygen atoms here sometimes they are getting single bond character, sometimes they are getting double bond character. Why? Because of the resonance, and that's why it has been observed the sulfur oxygen bond length as the intermediate bond length between single bond length and double bond length, and this is due to resonance. So this is a very important question can come, that why the sulfur oxygen bond length is in between single and double bond length. The answer is this is due to resonance, and you have to draw the resonance structures of sulfur dioxide. Now, what are the oxides of sulfur and their structures? Sulfur mainly exists in some oxoacids like sulfuric acid H2SO4, sulfurous acid H2SO3, pyrosulfuric acid H2S2O7, and peroxodisulfuric acid H2S2O8, where oxidation state of sulfur are given as +6, +4, +6, +7. You can calculate by simple way. You know the way of calculating the oxidation state of central atom or oxidation state of any atom in a compound, right? So these are the structures of oxoacids of sulfur, where you can see that the structure of sulfurous acid is like this, pyramidal shaped structure. Sulfur is connected with one oxygen atom by double bond and 2 OH group by single bond, and it contains a lone pair. In case of H2S2O7 or pyrosulfuric acid, or it is called oleum, the SO3H group, you can easily see this part, as I am pointing out. This part is a SO3H unit. This SO3H unit, this is one SO3H unit, and this is another SO3H unit. These two SO3H units are connected by an oxygen atom, and this is the structure of pyrosulfuric acid. Moreover, in case of H2SO4, H2SO4 has a tetrahedral structure where sulfur is connected with 2 oxygen atom by double bond and 2 OH group by single bond. In case of peroxodisulfuric acid, the SO3H unit, this is one SO3H unit and this is another SO3H unit. These two SO3H units are connected by a peroxide bond. This is a peroxide bond, oxygen-oxygen single bond. So these two SO3H unit are connected by a peroxide bond. That is why it is called peroxodisulfuric acid, H2S2O8. So here, what is the most important part? The most important part is the structures of these oxo acids and what are the oxidation states of sulfur in these compounds. Now, sulfuric acid and its preparation. Sulfuric acid is a strong dibasic acid because there are two protons in the structure of sulfuric acid, right? H2SO4. So sulfuric acid is a dibasic acid. It can donate two protons, right? So in case of donation of the first proton, H2SO4 will be decomposed into H plus and HSO4 minus, and dissociation constant of this process is Ka1. In case of second process, HSO4 minus is converting into or is decomposing into H plus and SO4 2 minus, and the dissociation constant of this process is Ka2. Now it has been observed that Ka1, the dissociation constant for the first process, is much larger than the second dissociation constant Ka2. Why is it so? This is because in the second process a dinegative charge SO4 2 minus is being produced from a single negative charge HSO4 minus, and that is quite a difficult process because this is the generation of the dinegative charge from a single negative charge species. Always chemical species always try to avoid charges, right? So here a dinegative charge is a species of dinegative charge is being produced from a single negative charge. Obviously this process will be very much difficult process, and Ka2 dissociation constant for this HSO4 minus will be much less than Ka1. Okay, so what is the structure of H2SO4? The structure of H2SO4 is this, where sulfur is connected with 2 oxygen atom by 2 double bonds, and at the same time it is connected with 2 OH group by 2 single bonds, right? So this is the structure of H2SO4. Now let's come to the preparation of H2SO4 by contact process. This is the most important part of this topic. H2SO4, in many years it has come that write the preparation of H2SO4 by contact process. So this preparation of H2SO4 by contact process involves the following step. In step 1, sulfur is burned, okay, to generate sulfur dioxide. It is a normal burning process where sulfur is burned in oxygen to give sulfur dioxide, SO2. In the second step, the SO2 that is formed in the first step is being reacted with oxygen in presence of catalyst V2O5. This is a very slow process. That's why a catalyst is used. Vanadium pentoxide V2O5 is used in this process, where sulfur dioxide is combining with water to form sulfur trioxide, SO3. In the third step, the sulfur trioxide that is formed in the second step is absorbed by concentrated H2SO4 to form a species that is called oleum. We have already discussed the structure of oleum, H2S2O7. So in the third step, what is happening? The sulfur trioxide that is formed in the second step is absorbed by concentrate H2SO4 to form oleum. Now in the fourth step, the oleum that is formed in the third step is diluted by simply adding water to generate a required concentration of H2SO4. Okay, we know what kind of desired concentration, what kind of concentration we want, or what is the desired concentration of H2SO4 we are trying to make, right? So what we have to do, we have to dilute this H2S2O7 by adding a suitable amount of water to give required concentration of H2SO4. So this is the total process of formation of H2SO4 by contact process. So these are the topics of group 16 elements. Hope you have understood all the topics. See you in the next video. Till then, thank you so much for watching this video.